Welcome to Unit 1, Lesson 15. This, my friends, is an introduction to complex numbers. There, I said it. Just like that friend you had when you were 4 years old, we are going to start talking about things that are imaginary. Yes, I know about you when you were 4 years old and your imaginary friends. Now, we cannot go into imaginary numbers until we get a little grip on simplifying radicals. This should be review. I'll do the first one kind of slowly, and the second one maybe even. But as soon as we start getting past that, I'm going to go through these quickly. So if you want to pause this, do them, then check your answers, you're fine. So how do we simplify radicals? Well, there are a couple ways, okay? And I will show you both ways for the first one. And I will always use one of the two ways myself, okay? Some people like to do a factor tree, meaning you just start finding factors of things that work. Let me explain that. What are two factors of 32? Well, 32 is, I know what goes into 32. 4 goes in there, 20. It's a 4 and 8. Yeah, 4 and 8 is 32. So I can say radical 8 times radical 4. Okay, and then I could do this. I have radical 2 times radical 2 is 4. And I can say this and this is radical 2 times radical 4, because 4 times 8 is 2. And this, my friends, 4 turns into 2 times 2. To me, this is a lot of work, okay? But then you're taught, well, if I compare these off, this turns into the number 2. This turns into the number 2. So I multiply all my leaves, so to speak. I take 2 times 2 times radical 2. And that would give me 4 radical 2. All right? And that's the answer. That's what radical 32 is simplified. And people that use this method really aren't good with finding factors. Okay? They can find factors and then, find more factors and find more factors. And when I pair things off, like radical 2, if I have 2 of these values, radical 2 times radical 2, the radical goes away and it becomes 2. Okay, they're good at that. Now what I like to do, okay, and I'll do this off to the side here. I like to take radical 32 and I try and find the biggest perfect square that goes into it. Okay, it's 16. Okay, so 32, that's the same thing as saying radical 16 times radical 2, because 16 times 2 is 32. And what's the square root of 16? It's 4. So my answer is 4 radical 2. To me, this is so much easier. It's the same answer. It's less work. It's less writing. But some people can't look at that and right away immediately say 16 goes into 32. If you can find the biggest perfect square that goes into every number, your work will be much easier. Okay? So, let's look at number 2 here. I'm going to do this my way. What multiplies by 48? That's a perfect square. 16 times 3. Since my 48 is under a radical, these two need to be under radicals. And the square root of 16 is 4. And this just comes down. Done. All right. Let's take a look at 18. Well, what multiplies to be 18? 9 times 2. The square root of 9 is 3. I can do nothing with my radical 2, so it stays. But look at here. That was negative. I can't just drop that. That comes along for the ride. Okay, so you see what we're doing here? You see what we're doing here, children? Children? Okay, number 4. Okay, well, let's look at the radical 200 first. That's 100 times 2. And this 2 just comes along for the ride, much like my negative did in the previous problem. The square root of 100 is 10, I can do nothing with radical 2, and I'm multiplying that times 2. So I get 20 radical 2. Good, 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 good. Now for number 5, adding and subtracting, what we call combining. Combining radicals is much like variables. There needs to be like terms, meaning if I have an x and I add a y, I cannot combine those. But if I have an x and an x, well, that's 1x and 1x. That's 2x. I can combine them. Radicals are much in the same way, very similar to variables in that matter. What do I mean? Well, I can combine radicals only if they're the same. I can take radical 2 and add radical 2. Well, I have 1 radical 2, and I have 1 radical 2. That's 2 radical 2, okay? I cannot add or combine radical 2 and radical 3 because they are different, okay? So when I see a problem like number 5, my hopes is that when I simplify the square root of 12 and the square root of 27, that what's left over will have the same number underneath that radical, so I can combine everything into one term. Let's take a look at this. I have 3. This is the square root of 4 times the square root of 3. Okay? So I have 3. The square root of 4 is 2. Radical 3. I end up with 6 radical 3. Plus, all right, let's see this one. I have 5. 27 is the square root of 9 times the square root of 3. Hey, hey, hey. So I have 5 times the square root of 9 is 3 times radical 3. That's 15 radical 3s. 6 radical 3s plus 15 radical 3s is 21 radical 3s. Woo! Nice. All right. Multiplying, multiplying, multiplying. Well, just like I can take, let me scroll up here for a second. Just like I could take, oh, here come the highlighters. Didn't think I was going to use them, did you? Just like I could take 48 and break it up into 2 numbers under radicals, okay? I can also take 2 numbers underneath radicals and put them back together into 1 number under a radical. Okay, 8 times 3 is 24. Okay, now I'm going to simplify the square root of 24. So I know that is 4 is the biggest perfect square that goes into that. Okay, so that's 2 radical 6. Yes, 2 times 3 is 6, but there is not a perfect square that goes into 6. All right. Now, someone once asked me, can I simplify this first and then multiply it times radical 3? You sure can. So that's the square root of 4 times the square root of 2. That's the square root of 8. That's 2 radical 2 times radical 3. Well, now I end up with 2. And when I multiply 2 times 3, under a radical it stays. And they are the same. So yes, you could have done that either way. All right? You could have done that either way. I always get amazed when kids are like, I did this another way, mister, and I got the same answer you did. And they show me, and I said, yes, you can do it that way. You're brilliant, son, brilliant. All right, on to the next one. Number 7, let me remind you of a rule with fractions and radicals, okay? It's a little too far. I'm just going to write this off to the side. You don't have to. I just want you to see this. If I have the square root of 2 values, okay, I can put them under 1 radical, okay? I can put them under 1 radical. I can take that fraction and put it underneath 1 radical. If I have radical top over radical bottom, okay, and they're the same root, they're both square roots, I can put that 1 fraction underneath 1 square root. And vice versa. If I had the square root of a over b, I can break that up and say square root of a over square root of b. That works both ways. All right? So I'm looking at this right now, and I'm looking at number 7. And I say, man, you know what would be cool? If I could just take 48 over 6 without a radical. And I can. I can convert this into that. I can put one fraction under the radical. And why do I do that? Because 48 is divisible by 6. It's even. Okay, 48 divided by 6 is 8. And what's a square root of 8? Anyone? Anyone? Euler? Anyone? That's the square root of 4 times the square root of 2. And the square root of 4 is 2. And there you go. Made life easier knowing our little rule about fractions. All right, next one. Ooh. I don't think you can really do too much of anything here. Well, maybe a little bit. Let's see. All right, I'm going to distribute in my radical 2. So it's 3 times radical 12, because radical 6 times radical 2 is radical 12. Minus radical 10. How come that's radical 10? Because 5 times 2 is my 10. I really can't, there is no perfect square that goes into 10. So I can leave it like that, but let's get a little bit more practice in here. The square root of 12, that's 4 times 3. I still got my 3. The square root of 4 is 2. Radical 3, and I still got my 3. So I have 6 radical 3 minus radical 10. That's it. Because what did Visca say about radicals? They're a lot like variables. If these are not the same, I cannot combine them. Okay? Oh, lovely, number 9. Lovely. We have to square something. Please, for the love of God, I say this every time this comes up. Does not equal 2 squared minus square root of 2 squared. No. Whenever something is squared, you need to multiply it times itself, not just distribute the 2. Okay? So it's 2 minus radical 2 times 2 minus radical 2. I am taking this and multiplying it by itself, which means we are foiling. 2 times 2. That's 4. All right? 2 times a negative radical 2. Well, a positive times a negative is negative. And 2 times radical 2, well, that's just 2 radical 2. Okay. I've got the same thing right here. Okay? 2 times negative radical 2 is the exact same thing. And last but not least, I have a negative radical 2 times a negative radical 2. A negative times a negative is positive. Radical 2 times radical 2 is the square root of 4, which is 2. Nice. That worked out well for us. So let's combine everything that we can. All right. I see a 4 without a radical and a 2 without a radical. That's 6. And minus 2 radical 2. And another minus 2 radical 2 would give us minus 4 radical 2. Look at us go. It's like we know what we're doing. Scary. It's a little scary. All right. Not too bad. And this all should have been review. Now, when I introduce you to imaginary numbers, I like to take the Apple Corporation route. A math teacher would understand that little pun there, root. Anyways, first you have your iPod. Oh, man. iPods were awesome. They were about the size of a charge card. But they're like, or a student ID, the same size. But if you stack like 4 or 5 of them on top of each other, they're that thickness. And you can put music on here, and you can like kind of spin this little thing right here. You spin this to make this little blue thing go up and down, left and right. Then you click things and you play music. And man, they had 60 gigabyte ones, and you're like, oh my God, it's so much. I can put on so much music. It was awesome. So first, we had our iPod. All right. After that, we had our iPhone. You mean I can call someone and there's no buttons, like physical buttons I press? I just touch the screen and the screen knows I hit a number? No way. Oh, these changed the world. I remember when my buddy got one of these and I still had a phone that it wasn't a smartphone. And it was a cell phone, it was a smartphone. My buddy's like, I just got one. I'm like, is it really like how it is in the commercial? He's like, dude, it is just like that. Because sometimes, you know, in commercials, they try and make things look better than they actually are. We've all fallen prey to that. But I'm like, is it really good? He's like, man, it is just like that. Then I got my hands on one. I'm like, I got to get into this craze. Of course, I'm a Samsung guy. I'm not an Apple guy. Sorry. Or, you know, sorry for you because I like Samsung better. You stink. Now, we have the iPod. We have the iPhone. And then we have the iPad. Oh, my God, it's a phone as big as your face. You can't call with it. But, I mean, you probably could with the right app. You could definitely text with it. But it was cool, man. It was a computer. It was revolutionary. And then we have our I number. We have our I number. Let's see if this is still on here. Is it going? Oh, there it is. Let's see. Let's wait for it. That's for you guys. You probably can't hear it in the mic, but let me raise that up. We have the I number. Wait for it, wait for it. Oh, yes. It's the imaginary number I. Oh, I love introducing that. It's not as effective. Wolfgang Amadeus Mozart. Okay? You know, it's better in class when I'm doing something stupid like dancing or whatever, or acting like it's really a big deal. But we have the I number. Okay? That's an imaginary number. Right? What does that mean? Well, I'm glad you asked. Right? The imaginary unit I is defined as the square root of -1. If I try to put a negative number underneath a radical in the calculator, I get an error. Okay? I can change the mode in the calculator. We won't get there right now. But you can now handle negatives under the radical. All right? What I tell my students is the following. The negative just pops out and becomes an I. So that's I square root of 1. What's the square root of 1? It's 1. 1 times I is I. And that's the way I tell my students to handle it. It's easier, just the I pops out from, or excuse me, the negative pops out from underneath the radical and just becomes an I. And then the negative under the radical is gone. Okay? So what is enormous is this. I squared is -1. How do we get that? Well, in order to get rid of my square root here, don't I have to square the side? So bang, bang. And if I square one side, I have to square the other. So I squared is -1. And that comes into play quite a bit, and you will see as we get going here. Now, basically, for any positive number, because we were just getting factors before. Remember when we had 32? And it was 16 times 2. We just did that in the warm-up problems. This is like saying -1 times a, right? Which we have here, which we have here. And the square root of -1 is just I. Okay? Now, you might be looking at that like, okay, I kind of get it. Again, what I tell my students is this. Pop the negative out, and it becomes your I. So now I've got an I. The negative is gone, square root of a. Okay, just have the negative pop out and become the I. That just solves all life's problems. So let's try some of these. Okay, this first one, the negative pops out, and I get I radical 9. What's the square root of 9? 3. 3 times I is 3I. There you go. Bam. Super duper. We're smart. SMRT, smart. I left the A out on purpose. Did I? All right. 2. Well, the negative pops out. That becomes I radical 7. Can I simplify radical 7? No. No, you cannot. There is not a perfect square that goes into 7. That is done in all of its glory. Love it. The square root of negative 18. The negative comes out, becomes the I. We did this. This is radical 9 times radical 2, isn't it? Times my I. This becomes 3. 3 times I, radical 2. Look at us go. Man, we're smart. Oh, God. Why aren't we in calculus yet? Issues. Issues. That's why we're not in calculus. In fact, right now, I would like to show you something on the calculator. Okay? I once said earlier that if I try to take a square root in a calculator of a negative number, we just said the square root of negative 9 should be 3i. Okay? But in the calculator, if I hit enter, I get an error. I say, well, go to my error. And it tells me non-real answer. Right up top here, it tells me non-real answer. Right there, yep, that's okay. Would it do that? Where's the point? There you go. Error, non-real answer. So if I hit 2, enter, go to my, where the error is, it puts me right in the front of the radical because there's a negative there. If I go to mode, the reason I get an error is because my numbers selected are real numbers, not imaginary numbers, where this black box is, okay, blinking right there. But if I move over 1, a plus bi, forget about the next one. That's a plus bi. I is an imaginary number. Okay, so now I've selected to use imaginary numbers, and if I take this, 3i. Oh, it's a beautiful thing, these calculators. In fact, didn't we say I squared is negative 1? Above the decimal point in blue is I. I squared should give us negative 1, shouldn't it? Yahtzee. Oh, oh my Lanta. It's so nice. These calculators do so much for us. And they're nice to know these things to check. But you really, if you want to be good at math, I mean, you want to walk into the room and people will be like, ask Bill. Bill's smart. He knows things. Because you know math. You should know math. And you should only use this for checking purposes. All right? But, you know, anyways, it's good to have this blanket of security here. Let's, I don't want to quit. Let's just clear this. Clear. Let's get back to our thing here. And let's go on to the next one. Okay, the cyclic nature of I. Okay, it's okay. I always ask my students this very first question. What is anything, love me the highlighter, what is anything to the power of 0? And I always get, well, not always, but most of the 0. No. Anything to the power of 0 is not 0. It's 1. Okay? What is anything to the power of 1? Itself. 5 to the power of 1 is 5. 13 to the power of 1 is 13. I to the power of 1 is I. Okay? Here's the big one. I squared. We've already said that's negative 1. And I cubed, believe it or not, is negative I. How come? That happens when you take I times I squared. Okay, because remember, don't we add exponents? We do. 2 and 1 is 3. Well, this is I times negative 1, because we just said I squared is negative 1. And negative 1 times I is negative I. Is that important to know? No. If you know these 4 right here, you are good to go. Because what happens? Cyclic. It means it repeats. There's a cycle. I to the 4th is 1. I to the 5th is I. I to the 6th is negative 1. I to the 7th is negative I. If I were to go to I to the 8th, guess what it would be? 1. Then I, then negative 1, then negative I. It repeats that cycle. Those 4 values. 1, I, negative 1, and negative I. It repeats. 1, I, negative of 1, negative I. 1, I, negative 1, negative I. It repeats in cycles of 4. So, why is that significant? Because they're going to tell you to simplify something like I to the 32nd or I to the 17th. Okay? And how do we simplify that? Okay, here's an example. How do we simplify that? I take n and I divide it by 4. And I'm going to get an answer. I get a quotient, which is the answer. It's something. And then I get the remainder, right? Whatever the remainder is becomes your new exponent. Okay, listen to me for one moment. If I have I to the 18th, okay, I take 18, I divide it by 4. It goes in there 4 times with the remainder of 2. This becomes your new exponent, and I squared is negative 1. Okay? How is that? Because if I did this pattern, I to the 5th, I to the 6th, I to the 7th, and so forth, and did it, then did another 4, then another 4, I to the 18th would be right across from I squared. Remember, there's 4 terms, so I'm going to divide by 4. And whatever my remainder is becomes the new exponent. Okay, so just trust this one. Even if you don't understand what I just said about how the 18 would be across from the I squared, trust this process right here. Divide it by 4. And whatever your remainder is, this is the new or the current exponent for your I. Okay, whatever that remainder is. All right. And if you multiply 2 imaginary numbers together, you can get a real number. Can you? Sure. Isn't I times I 2 imaginary numbers? That's I squared. Doesn't that give you negative 1? Negative 1 is a real number. Sorry, people. You already knew that. Okay, operations with I. Let's start doing some of this stuff right here. We have I to the 7th, and they want us to simplify that. Well, I to the 7th is just I to the 7th, man. No. No, it's not. How come? Because I'm going to take 7 divided by 4. It goes in there 1 time with a remainder of 3. 3 becomes your new exponent. And I cubed is, it's not negative I. It is negative I, isn't it? It's negative I. So if you need to, write this down real quick. Okay, write that down. So I can say, if I'm doing all these things here, I say, okay, I to the 0, that's 1. I to the 1, that's just I. I squared, that's our golden child. And I cubed is negative I. So if you want to write this off to the side, I mean, that helps. There's no rule saying you can't refer to your notes. I want you to refer to your notes to the point where you get it. Okay. Second one here. I have 2. Whenever I multiply 2 things together, don't I add the exponents? So that's 3 plus 11. That's going to be 14. Now, I take my 14, I divide it by 4. That goes in 3 times, okay, which is 12, and a remainder of 2. This is my new exponent. So it is 2 times I squared. What is I squared? Negative 1. So it's 2 times negative 1, which is negative 2. Woo! Good. Good. Stupendous. Love it. Love it. All right. Next one. We have 4. I'm going to add 5 and 15 to give me 20. 20 divided by 4, it goes in 5 times, the remainder of 0. So that's like 4 times I to the 0. I to the 0 is like 1. 4 times 1 is 4. Very good, very good, very good. You know, children, we're done multiplying and now we have to add. And I can't just add these things, so I'm going to have to evaluate these separately. Okay? Adding is different than multiplying. Multiplying, I can multiply anything together, but I can't add everything together. Okay, remember, radicals need to match, just like variables, in order to combine them. In order to add or subtract them, they need to be the same. Okay, so it's my hopes that when I simplify these two imaginary numbers, I have the 13 and I have the 9, hopefully I get the same value of I left. If I don't, I just got to leave them separate, meaning if I had x to the 13th and plus x to the 9th, I can't combine those. If I had x to the 13th and x to the 13th, I could. Okay, so let's simplify these bad boys. Okay, I am going to take 13 first. Highlighter, highlighter, how I love you. Bam. And I'm going to say, okay, 13 divided by 4. It goes in there 3 times with a remainder of 1. So really, this is like 12 I to the first. Okay, I don't have to write an exponent of 1 if I don't want to. Plus, okay, now I'm going to take my 9. Highlighter, highlighter, where did you go? There you are. All right, so I have 9 divided by 4. It goes in twice with a remainder of 1. So now I've got 2. Wow, that was weird. Look at that. Would you look at that? Would you look at that? Okay, now that is 2. Oh, now this is all going to be off. I to the power of 1. And that is, wow, that's like 4 inches higher than it needs to be where I'm writing it. But well, I'll adjust that. I'll hit pause. And that's going to be 14I, because now I can combine that. Let's see how good. Oh, my goodness. 14I. 12I plus 2I is 14I. Very good, very good. Oh, I am so off. When I went to hit pause, it minimized it. In fact, I think this is a good sign. We've been working for about 32 minutes. Let's stop here for part 1, and we'll come back, and I'll see you again for part 2. In fact, if you want to start doing some more of this packet and watch this video later, by all means, check to see if your work is done and done correctly. And if not, we can see where you made your mistakes. Because it is easier to help a student who has work done and tried something because I can see where they went wrong, as opposed to a student that comes to me and has nothing done because I have no clue what's wrong with them. Well, I can't do anything. Well, then we should really assess your life choices. I'm teasing. I'll see you next time for part 2. Bye-bye.